All right, let's dive into one of the biggest ideas we use to understand ourselves, the brain as a computer. It's a really powerful analogy, right? It helps make sense of that 3-pound universe sitting inside our skulls. But, how far can we really take that comparison? Let's find out. So, I'm going to start with a pretty wild question. Is your brain just a super advanced computer that happens to be made of meat? It's a fun thought, but it really gets to the core of what makes us us. To figure it out, we're going to build this analogy up piece by piece, and then we're going to watch where it just spectacularly falls apart.
Okay, first things first, let's see why this whole brain as a computer idea is so popular. And honestly, at a high level, it's a fantastic way to get a handle on the basics. I mean, both systems process information, right? They take in data from the world, they chew on it, they make decisions, and then they produce some kind of output. It makes the super complex feel kind of familiar.
And if you look at this, you can see just how neatly the parts seem to line up. Your frontal lobe, where all the big decisions happen, that's basically your computer's CPU. Your senses, your eyes, your ears, they're just input devices, like a camera or a microphone. Your memory? Well, that's your RAM and your hard drive for short-term and long-term stuff. Even your sleep-wake cycle acts like a power supply, and your muscles are the output, like a printer or a robot arm. On the surface, it's a pretty convincing match, isn't it? So that's the big picture hardware. But now let's zoom in a little bit. Let's look at the actual language, the code, that both of these systems are running on. Because when you get right down to the very, very basics, your brain and a silicon chip work on a principle that is shockingly similar. It's all about a simple, universal language of on and off. This is where the digital world and the biological one seem to speak the exact same language.
Think about own binary code. A neuron is either firing a spike, that's a 1, or it's sitting quietly, that's a 0.
And these signals are unbelievably fast. Each one of those little electrical spikes, each action potential, lasts for just 1 millisecond. That is 1,000th of a second. It's this rapid-fire binary code that lets information just zip through the massive network of your brain, letting you think and react in a blink. So up to this point, the computer analogy is holding up great. It's looking really solid. But now we've reached the point where it all starts to break down, and this is where the real unique magic of the brain starts to show itself. This is where biology totally outplays silicon. See, the brain isn't just an electrical machine. There's a huge difference in how its parts are actually connected, and that difference introduces a whole new universe of complexity and nuance that no computer on Earth has. And that huge difference, it's called the synapse. In a computer, everything's connected by physical wires. The electricity flows right through. But in your brain, neurons don't actually touch each other. There's this tiny, microscopic gap between them, the synapse. And that gap isn't empty. It's a chemical space. And that, my friends, changes everything. So how in the world does a signal get across this gap? Well, it's this really beautiful 4-step dance. First, an electrical spike zips to the end of a neuron. That arrival makes that neuron release these tiny chemical messengers, which we call neurotransmitters. These little guys float across that synaptic gap, and they lock onto the next cell, which then triggers a brand new electrical signal. So the signal goes from electrical to chemical and then back to electrical again. That is something that is uniquely, beautifully biological. Now, this whole electrical to chemical switcheroo isn't just some neat little factoid. It is the very thing that governs our decisions, our moods, our deepest desires. Let's make it real with an example we can all relate to, the simple daily battle of a craving. So, picture this. You're walking past a bakery. You see a perfect slice of cake in the window. Instantly, inside your head, a massive debate kicks off. To eat the cake or not to eat the cake? But this isn't a logical, rational debate. Oh no, it's a full-on chemical competition. So here's what's happening. Some of those chemical messengers, those neurotransmitters, are excitatory. They're the yes votes. The amazing smell, the fact that you're hungry, how delicious it looks, all of that releases yes signals. But at the same time, other neurotransmitters are inhibitory. They're the no votes. The thought that you're on a diet, that it costs too much, maybe you're even allergic to the nuts on top, those are all no signals, trying to hold you back. In your final choice, it is simply the winner of that chemical tug of war. If the yes signals are stronger than the no signals, you're buying that cake. If the no votes went out, you walk on by. Every single choice you make, from what to wear to who to marry, is the result of a chemical competition just like this one.
But these chemical battles aren't just happening for no reason. They're not random. They are all working in service of something much deeper, something ancient, the brain's core biological programs.
That's right. Every chemical tug-of-war, whether it's about a piece of cake or asking for a raise, is being guided by a set of deeply ingrained biological needs. These are like the master programs that our brains are constantly trying to run, no matter what. The physiologist Pavel Simonov actually gave us a brilliant way to think about these core drives. He put them into three main buckets. First, you've got vital needs, the absolute basics for survival: food, water, safety. Then there are social needs, the drive to find a partner, care for family, and figure out our place in the group. And finally, you have self-development needs, our built-in curiosity, our need for freedom and play, and how we learn by copying others. And here's the kicker. These three groups are always competing for control over what you do next. So in the end, your brain isn't a cold, logical computer at all. It's a dynamic, messy, amazing chemical machine, constantly balancing these ancient competing programs. So as you're sitting here taking all this in, let me ask you, which one of these core programs is driving you right now? Is it your need to learn and develop? Is it the simple need to save some energy? Or is it something else? That ongoing chemical battle, that's what makes you, you. And that is a level of beautiful complexity that no computer has even come close to matching.